Well, hello everybody. I'm going to talk to you today about an introduction to multithreading in C++ 20. For the purposes of this talk, I'm going to make a couple of simplifying assumptions. The first is that this is a new project. You're not trying to add multithreading to existing code where you've got particular requirements. And in particular, I'm assuming that you've got a nice shiny C++ 20 compiler and library. If you don't have one of those on your current project, then some of these things you'll need backports and to use things from Boost and stuff like that. Most things are around if you look for them, but they don't have the same C++ 20 syntax. So in C++ 20, then there's a few things. Firstly, I'm going to look at choosing your concurrency model. Why are you doing multi-threading and what sort of approach you're likely to take and how that impacts things. Then we're going to actually look at the C++ 20 facilities for starting and managing threads, and then crucially synchronizing data, because that is one of the things that is more involved with multi-threaded code. As if you have any experience writing multi-threaded code in using other libraries or other languages, then I'm sure you're aware. So for choosing your concurrency model, then really there are two reasons why you might want to use multi-threading and concurrency in your application. And whatever your other incidental reasons are, they fundamentally boil down to these two. And the first one is you want scalability. You've got a big problem to solve, and what you are wanting is, as you throw more execution calls at the problem, it gets faster. So this is very common if you've got HPC is the classic example of this, where you build a big computer, it's got 1,000 cores. That's not fast enough. Okay, we'll make it 2,000, 5,000. You just add more cores, your problem gets more tractable. And you want your application just to nicely get faster as you add all these extra cores. The second reason why you might use concurrency is because you know that your operating system can interleave multiple threads, and you have an application task that naturally fits in with things that can run concurrently, even if they're not really performance sensitive. So you've got aspects that that can run in the background, but you want to happen continuously in the background. And the separation of concerns that you get from having, I've got a dedicated thread to do this and a dedicated thread to do that, helps you in your programming and your overall application design. But you don't have enough individual tasks to fulfill 1,000 cores worth of hardware. You're looking at doing it from a programming design perspective rather than literally the raw performance and scalability. And obviously, in many real applications, you have some mix of these. You have some parts of your application which you want to scale because they're the heavy data processing bits, and then other bits where having a dedicated thread for doing background spell check or background underlining of compile errors in your IDE is a nice thing to have, but it doesn't necessarily need to scale quite so well. And so which of these we're using informs the way that we make our designs about our choices about program design. So it's important to work out which of these is the driving force for your application. If we're looking at scalability, then an important thing that you want to pay attention to is Amdahl's law. The speed up multiplier is 1 divided by our serial fraction, which is 1 minus our parallel fraction, and then our parallel fraction divided by the number of execution calls. And so you can look at this, you can see as p gets closer to 1, then your scalability goes up, and as the number of execution calls goes up, then your scalability goes up. So just to stick some real numbers in, if we've got 90% of our application can be parallelized, you might think that's a reasonably high percentage. And then say we've got 1,000 cores, then actually you're only going to get a 9.9 speed up, which isn't as much as you might have hoped. And so you might hope that you're getting somewhere near 1,000 times speed up, but it's that 0.9% that's getting it. Because even if we stick in 100,000 cores, we still don't get to 10 times speed up. It's still 9.999 at 90% parallelism. At 99% parallelism, we get that extra factor of 10 to 100, 99.9, but that's still on 100,000 cores. So you really, if you're after parallelism, you really need to be focused on, the problem needs to be parallelizable. We want to minimize that serial fraction. So that is something that you're absolutely looking for if you're wanting scalability. And if you're doing that in C++, then from a programming perspective, the easiest way to do that is to use the parallel algorithms. And most of the standard libraries that ship have support for these parallel overloads. How well they do will vary, and particularly depending on the data set that it uses. There is going to be no point trying to run a parallel sort if you're sorting 100 elements. It's not going to be worth it, because the overhead of managing the execution cores is going to take up all the time, and that's going to reduce the parallel fraction. On the other hand, if you're trying to sort 1 trillion elements, then it's probably worth it. Particularly if you do have an HP system with 1,000 cores, 100,000 cores, which incidentally isn't that daft. Even on a desktop, you can get desktop GPUs which have 100,000 cores. So if you have the support in your compiler for moving stuff to the GPU, then anything that can be parallelized, big data sets can be parallelized, and it's worth looking at these. Obviously, again, in practice, then how your program divides up. Now, if you use the parallel algorithm straight from the standard library, then they still execute those. The sort is done by the time it hits the semicolon, it moves to the next statement. So if you've got 50 steps, then what happens is you run your parallel for the first step, then you parallelize the second step, and then gather it all in, and then parallelize the third. And how that fits for your application overall those gather steps might actually impact the overall performance. And you might need to look at moving to additional libraries that then can chain the parallel operations without having to do the gather steps in between. If you're writing an application where this matters, then you might need to look outside the standard, because the standard only has this. Things like the HPX library from Stella, they've got some approaches to doing this, where you can chain your parallel operations. And if you look at things like the libunifx framework, which is the implementation of the executor proposals with senders and receivers, then again, that allows you to put structure in your concurrency and say, well, I'm running this algorithm, and then with the results, I'm running this other algorithm, and then I'm running the whole lot on my thread pool. And that sort of thing allows you to write your HPC code, but it's outside the standard. So yeah, and that's an example of writing independent tasks. If you're after parallelism, then this is fundamentally what you want trying to do. You want to split up into as many independent tasks as you can, and then have some form of thread pool that executes them all on your hardware. And we don't have those in C++20. We don't even have them in C++23, sadly. We were hoping we would, but we don't. So you're looking at third-party libraries, Intel threading building blocks, libunifx, HPX, that sort of thing. There are libraries out there, but they're not standard, sadly. Okay, so on the flip side, you're saying, well, yeah, I've got parallel hardware. I'm probably running on desktop, might have 16 cores. I'm wanting to utilize the hardware that's available when I can, but it's not crucial. I'm not after that literal raw scalable performance. So what I probably have is I'm using threads to separate my concerns. I have a few, maybe a few dozen things that are running concurrently, but they might actually be competing for resources rather than trying to use them up as best we can, or they might be blocked on I/O or something. So you're not the raw performance is not directly the effect that you're seeking, but obviously you're hoping that you'll get better performance with more cores, but you're not looking for that direct scalability. And in this case, then this is something where the C++20 library can help you. Use JThread to manage your tasks, and you start your tasks on different threads. You might have a thread running the GUI, you might have a thread doing printing, you might have a thread doing background compiling, or a thread doing I/O, all the things that you want to divide up, and then you can just create a separate thread for each using JThread. And you just pass it the thing that you want to run, and it starts a thread for you. It's very straightforward. So, that would naturally lead into the next part of starting and managing threads. But first, I want to take a detour into cooperative cancellation. So, if you're running a GUI, there'll be a cancel button on anything that takes a bit of time because, oh, I didn't really mean to download that file. It's going to take 3 hours. No, cancel that. Oh, it's going to take you, 5 minutes to do this relayout. So I don't have time to re-render this. Cancel, whatever. So you want, if you started that in a background thread, you want to cancel. Obviously, you don't need a GUI to want to cancel things. You might have started a network transfer and decide that you don't need it, or whatever. But the idea is that though thread libraries will provide you a means of forcibly stopping threads, or at least the raw OS ones do, then you don't want to do that because that leaves your programming overall in an unknown state. You forcibly stop threads, you don't know which resources that thread owns, whether they've been properly freed, whether they're in a state where other threads can use them, or whether they're saying, well, only that thread can use it. But no, that thread doesn't exist anymore. Well, now that particular resource is unusable. So what you want is something that allows you to say, please cancel this operation that's running on a thread, and then the other thread stop its operation, do the cleanup, and then release the resources, and so that overall your system proceeds. In C++20, we have two types that help with doing this. We have a stop source, which is a source of stop requests, and a stop token, which allows you to check whether someone has requested that you stop what you're doing. And I emphasize that this is purely cooperative. If somebody makes a request for stop and you don't check, then nothing happens. You have to explicitly say, I want to stop. So typically the usage is you create your stop source, you get a stop token, you pass the stop token around to whatever it is that you wish to actually stop or interrupt on a cooperative cancellation method. Then you call request stop and say, please stop. And at some point, that task will actually say, has somebody actually asked me to stop? And then presumably you then write it to do something that actually stops doing the task. And again, if you do not check where the stop has been requested, then all this mechanism has no effect on your program. It is cooperative, not forced. So let's put that in some code. We have our stoppable function that takes a stop token, and it's going to do a while loop. And while we haven't had a stop requested, we're going to do some stuff. And we're going to keep doing stuff until someone tells us to stop. And then we have another task that has a stop source, and it's going to have a little loop. It's going to do something until it's done. Maybe that interacts with the stuff that the other thread's doing. Maybe it doesn't. But then when our stopper task has finished whatever it was doing, it's going to say stop. And at this point, then the stop token will have its flag set. When stoppable func checks has stop been requested, it will get returned true. It will break out of its while loop and it return. But note that the stopper task returns immediately. It sets the flag and returns. It doesn't wait. If you want to wait, then you have to use something else to wait for the task. This is just I'm going to set my flag and carry on. Right? So there's no backward synchronization there about whether or not something has actually stopped. You just make the request and then hope that the person who's responsible for writing the other piece of code actually honors that request. Obviously, if that's you, then you can make sure, but if it's your colleagues, then you have to hope that when you give them the stop token, they actually use it. You don't have to integrate stop tokens directly into everything in order for this to work. If your library or OS has, for whatever facility you're using, has a mechanism of interrupting it. So if, for example, you have an IO mechanism that has a cancel IO function, then you can make that integrate with stop tokens by using a stop callback. So you create your stop callback, given it a stop token and something to run. When another thread requests that, makes a request on the source associated with this stop token saying, please stop, then your callback will be run. And so in this instance, we're reading a file, we have our stop token, and we open a file with a file name, we've got a file handle. We then create a stop callback that says, if someone asks us to stop, please cancel the IO on this handle. And then we're going to do our read. Now, this can be a blocking, in this particular model, I'm thinking this is a blocking read, but if some other thread calls cancel IO, then it will interrupt that read and then it will return. And so when another thread calls request stop, then it will say, there's a callback registered for this stop token. So please, at this point, I'm going to invoke this cancel function. Now, note, this is called on the thread that calls request stop. So you need to make sure that it's not too heavy a function that's going to cause big blocking delays on the other thread, unless obviously you've coordinated in your team that that's okay. But you need to make sure that it's not something that's going to epically delay the function that's requesting stop. But it will call your callback and therefore cancel the IO, and then your read data will return, and then it will unregister the callback so that and then carry on. So it's carefully done so that it's synchronized, so that if there's a race between trying to unregister the callback and the cancel on the other thread, then it will make sure that it all resolves nicely, and either it neatly happens that the cancel is called before the callback is destroyed, or it's not called because the callback's been destroyed first. You don't have to worry about that. That's all synchronized. It's just that you have to work out what is it that if there is this function cancel IO that you can call, you can use a stop callback. Now note, this is actually a template, and it is using the argument deduction in order to associate with whatever callback type you put. So there's very little requirements on that callback. It doesn't have to be copyable and all these things. It can just it can be pretty much anything that you can invoke, and it will deduce the right type and save it in the callback. So I think this is a really, really useful feature attached to this token, because it makes it not just a very specific, I have to manually check for this, but it allows it to integrate into pretty much any library that has any mechanism of interruption. If you have a library that uses an alternative set of stop tokens, because they call them cancellation tokens or something after the .NET library, then you can use that, because you can create a cancellation token and then you can call it with a callback, register a stop callback that signals the cancellation token. So you can integrate this with any mechanism that you have that will actually do that interruption. Okay, so little aside finish there for a minute. Now we'll actually look at starting and managing threads. And I will say, if you're using a C++20 library and you're managing threads yourself, in 99% of the cases, you want to use JThread. And this is the new thread class introduced in C++20. This is what you should use. Occasionally, you might want to use standard async, which is a C++11 feature. This is for the case where your thread is going to return you a result, and you want to actually, you're going to wait for the thread to finish, and you want the result that it's going to give you. But it's, in practice, it's quite rare that that is how things work out. Mostly you're going to want results ongoing from your thread at various points, and so having a single result at the end is not what you want. But if it is, standard async is your friend. And then finally, well, there is standard thread from C++11, but really, if you've got C++20 compiler, you probably don't want to use it. There might possibly be an occasion where you have to, because you've got you're using another library that expects you to give it a standard thread to look after. But we did say at the start that we're expecting your new project, so these sorts of restrictions are likely to be less. So probably you should not be using standard thread, but it's there if you do need it. So how do we use our JThread? Well, when you create your JThread object, that starts the thread. And you give it a function or callable to run and some arguments. And it will run your function with the arguments, and also as a first argument, it will give you a stop token. So it is directly integrated with our cancellation mechanism. So if you run a background thread, you have a stop token that is just given to you there by the JThread, so you can use for checking to see whether you've been interrupted or not. Of course, if you might not need that stop token, your callable might not use it, and then actually, if your callable doesn't accept a stop token, then it won't be given one. The JThread will just say, "Oh, you don't use it. Never mind. Here, just have the arguments you give me." So it'll just run your function with the arguments. So this does mean that you have to watch out. If your function can take variadics that will match against anything, then it will give it a stop token as the first argument. And if that then causes a nested compilation error, then, well, it's a compilation error and you'll have to figure out how to deal with that. But that's, in practice, again, that's rare. Mostly when you have a threaded function, you know what arguments it wants. It takes exactly these 5 or this one argument and possibly a stop token. But so the SFINA mechanism that determines this usually works. It's only, like I say, if you have a variadic function that literally accepts anything without constraints, that causes a problem. So the full basic API, we have our default constructor, which creates an object with no thread. This is what you get. Also equivalent, if you move the ownership around, then one of them will one of your objects will end up with no thread if it was moved from. You can create it with a callable and some arguments. If you do that, it creates a new stop source, and then it creates a new thread running your callable with its arguments and possibly the token obtained from that stop source. The destructor has a nice feature. It requests that your thread stops by signaling the stop token, and then it waits for the thread to finish. So this is different from standard thread, and one of the reasons why you should use JThread is that it has this automatic join in the destructor, and this is integrated with the cancellation mechanism. So if your thread is cancelable, then it will, and you destroying your JThread, it will then automatically cancel the thread and wait for it to finish, and then it all tidies up nicely, and everything is nice and clean, and it makes scoped management of objects that are referenced by your thread that much easier, because because we have that implicit lifetime management. Obviously, we can get the ID of the thread. It's a standard thread ID that you can use just for checking, is this thread the same as that other thread? Mostly it's used for logging purposes in the sense that you can stream it to standard out or any other row stream, and you can compare it to something else, and you can create a hash of it so you can use it as a key in a container. But it doesn't in any way necessarily relate to a thread ID that you might get from your OS or anything else. So you need to IDs are just used for, is this the same thread as this other thread, really, rather than anything specific. And then, of course, you can call join to wait for the thread to finish without having to destroy the object. So if you want to wait for it to finish at a particular point in time, then you can do that. Important thing to note is the handle. It's a value type and it's movable. It's not copyable, but it's movable. So you can transfer ownership of a thread between JThread objects. It means you can store it in containers. You can have a vector of JThread, and there is no need to use new. The number of times I've seen people write new standard thread, whatever. No, it's like, please don't. No, it's already a handle. You don't then need to dynamically allocate it. And obviously, if people are coming from something like Java, where that's just how you write objects, then maybe, but yeah, don't do that. There's no need. If you used C++ 11 standard thread, then this is no surprise. The callables and arguments are copied into the storage that's local to the thread before the thread is started properly. And so this, by default, avoids dangling references because you have copies of all the objects. If you really want to reference something, then use standard ref, because then the thing that's being copied is the reference wrapper. Alternatively, you can use a lambda with reference captures because it copies the lambda, but the reference captures in the lambda are still reference captures. So you can have references, but that's something to be aware of whenever you're doing threading, is you don't want the references in your thread to outlive the objects they refer to. It's easier to achieve that when you're using JThread to make sure that to wait for the thread to finish, but you still have that potential for dangling references. And of course, race conditions. If you've got a starter thread with a reference, then that reference can then be accessed by other threads. Classic mistake I've seen people make is they try and create worker threads, and they give each thread, they create a loop with an index variable, and they want to pass that index variable as an ID to the worker thread, and they pass it by reference. And so the first one has a reference to the index counter, and then the second one has a reference to the same counter. So now they both, when the counter is updated to A, it's a race because they're updating and the other thread's reading, and now they both still see the same value of the counter. So if you pass by reference, you need to watch out for that sort of thing, which is, again, why it's passed by copy, because if you pass the index as an argument by copy, then first thread gets 0, the next one gets 1, the next one gets 2. There isn't a problem. Okay, so in the destructor, then I already said it requests the stop and then waits for the thread. So we have our thread function that takes a stop token and it's running its loop. It's doing some stuff with the arguments you gave it. And then you've got our other function that creates a JThread to run that, and it does its own stuff. And then at the end of the scope, the destructor requests a stop and then joins. Now, obviously, this means that then by its very nature, this is exception safe, because if an exception is thrown in our function foo that's going to do stuff, then it will automatically then request that the thread is cancelled and wait for it to finish. And so it makes it easier to program and design for exception handling. If you're trying to do this with standard thread, then you wouldn't have an implicit stop token. You'd have to catch the exceptions and make sure that you then signaled stop and then joined, and it can be a mess. JThread makes it much easier if you've got a stoppable function. So yeah, this is one of the key benefits, is this integration with the cancellation. We implicitly create our stop source. That stop token is passed as our first parameter. If our thread takes it, if the function we give it doesn't, then it doesn't. It's okay. It's optional, and we get this request stop and the force join. But of course, you still need to check. It's a cooperative mechanism. You must check that stop token if you've got one. Otherwise, it does you no good. So there is like an additional few functions that are added to go with this. So we have our JThread that's created for some callable. We can get the stop source so that you can trigger that stop request without having to join with the thread immediately. You can use that directly. And you can get the stop token that is used so that when you request that thread is stopped, then also something else can also be stopped. You might have other tasks running on other threads that you want to interact with. And then you can just, rather than having to get the stop source and the stop token directly, you can just say request stop, and it does the equivalent of get that stop source and then request stop on it. Okay. Synchronization facilities. Now, most multi-threaded programs need to share state between their threads. If you don't need to share state, then this is great. You have nice, completely independent threads. But to some extent, why are they different threads in the same application if they're completely independent? And there's some cases where you started a thread, it's going to calculate something and give you a result back. And whilst it's doing its calculation, you don't need to interact with it. But oftentimes, then you have multiple threads and they're going to interact with each other during their lifetime. In which case, they're going to share data, and you need to watch out for data races. A data race is anytime you have unsynchronized access to the same memory location from two threads, and one of those is a write, which, if you don't have explicit synchronization, is pretty much any pair of accesses to the same thing. And the important thing is in C++, data races are all undefined behavior. And it really can cause big problems. It might seem innocuous, but you can, that undefined behavior is real. Most likely it will crash your program because just in general, that's the most likely output. But often you might find it's slightly gives you wrong values or gives you memory leaks or buffer overrun errors and security vulnerabilities. So you need to watch out for undefined behavior from data races. And the simplest way to avoid that is to make sure that you use proper synchronization mechanisms. And C++ has a bunch of these. We have latches, barriers for synchronizing groups of threads. We have futures for passing data around. We have mutexes as a general protection mechanism. Semaphores, which are an even more general synchronization mechanism. And then we have atomic operations for low-level synchronization. And I would say pretty much, this is the order that I'm going to explain them. B, this is the order that you should reach for them. If you have a problem that you can solve with a latch, use a latch. If you can't solve it with a latch, but you can use a barrier, use a barrier. If you need a future, because you're transferring data, use a future. If you can't use any of those, then use a mutex. If you really, really have a problem that a straightforward mutex doesn't solve, but you still need synchronization, then use a semaphore. And if you're doing something super low level, then maybe you want to use an atomic, but mostly you probably don't. In most programs, there will be a few places where it's best to use an atomic, and you should have someone on your team who knows how to do that and make sure that they can use atomics correctly. But most people shouldn't be using atomics. So I'll briefly explain them, but most people shouldn't be using them. Okay, so latches are first. And a latch is a single-use counter, and it allows you to wait for it to be triggered. If anyone's done electronics, then it's like a latch in electronics. It's like a physical hardware latch that once it's triggered, it latches and it stays put. So the point is, you give it a count, it counts down as threads say countdown. Here's a countdown event. When the count hits 0, it's triggered and it stays triggered forever. And at any point, any thread can wait for it to reach 0. If you wait and it hasn't, if you call wait and it's not yet 0, then you block until it does get counted down. If you wait and it's already 0, you wake up immediately. And it's one use as a consequence because it has this permanent latching mechanism. And so the API is really straightforward. We create a latch with a count. You can count down, you can wait, or you can combine the two with the oddly named arrive and wait, which is so named for coherency with barrier, which also has arrive and wait. But it ought to be called countdown and wait. But there we go. So if you look at it in some code, then you have a function, it has some thread count. We create our latch to say when we're done. We're going to create some data to go with each thread. So we have a vector of, well, optional data because haven't got any data yet. And we have one entry for each thread. Then we have our vector of JThreads, and we're going to create our threads. We're going to create our JThread. By default, we're going to capture by reference so that we can access this data vector, but we're also going to pass I by value. Again, we don't want dangling references to our loop counter. And so then each thread is going to make the data for its own slot, and it needs to know which slot it is, to stop which variable to access, and B, because its data is going to be unique to it. Then it's going to count down the latch, say, my bit of data is ready. And then it's going to do something else. So we're not waiting for the thread to finish. We're waiting for the thread to produce its bit of data. And so we have our countdowns sort of in the middle of the thread's lifetime. And then at the end of our for loop, then we're going to wait for that latch to trigger. So this says at this point, we know that all of the threads have got as far as creating their data and sticking it in the vector. And so we can now process that vector of data, and all is well. In the meantime, whilst we're doing that processing, all the threads are going to carry on and they're going to do their extra stuff, whatever that is. And the do more stuff that's remaining for them to finish. And then at the end of the closing brace at the bottom there, then we destroy our vector, which destroys the JThreads, which waits for them all to stop. So then everything tidies up and we're all done. My favorite use for latches is writing multi-threaded tests for something else, because it allows you to avoid any races due to the actual overhead of creating threads. If you're trying to set up a test case where you have 3 threads that are going to access your data structure because you're wanting to see, can I concurrently access the data structure? Can I push the data on from this one thread? Can I pop up data off from this other thread and do something else all at the same time in some concurrent fashion and check that it all still works without without problems, and that the errors that occur are expected and everything behaves correctly. If you just start your first, you write, JThread, thread 1, do this, thread 2, do that, thread 3, do the other. Depending on how the OS is feeling at the time, then it might be that your first thread actually has run to completion before it's even got as far as starting the second thread. And because actually starting a thread is quite a big, heavy operation. If you use a latch, then you can ensure that all your threads have been started. We've done this heavyweight start the thread operation, but they're not actually doing anything useful yet because they're waiting for the latch. So you create your thread, and the first thing that each thread does is arrive and wait on our latch. And so at this point, then when the last thread has been started and it's actually running some code now, and it's actually got as far as that arrive and wait, then the last thread that counts down with that arrive then triggers all the threads, and then they can all proceed all at once. And if you've got enough CPU cores, then actually they might well really start all at once, give or take a few microseconds. And so this is the best way that you have of controlling the scheduling of threads under test in portable code, because you can set up your environment as best you can, and then have everything wait on the latch. It's all ready to go. Boom! All your threads go at once, and they all execute the code that you're already trying to test, all in the right place. So that is my favorite pattern for latches. Okay, the next thing we have is barriers. Now, standard barrier is a template, and it's a reusable barrier. And it's a bit like a latch in that point is you have a count, and it's triggered when the count reaches 0, but it's phased. So whereas with a latch, any thread in the system can wait on the latch. For a barrier, then only the threads that are involved in the barrier, participating, I think is the word used in the standard, the participating threads can wait. And so they arrive at the barrier and then they wait. And when all the threads have arrived at the barrier, then the completion function is run, which by default does nothing at all, but you can give it something to do. And then when the completion function is finished, then all the threads are then woken up, and then they can proceed again, and then they can arrive at the barrier again. So we have this loop facility. It runs in phases. We run phase 1, then all the threads are arriving. When they've all arrived, we do the completion phase, and then we start the next waiting phase, and then they can all arrive again, and then they will all wait, and then they can run the completion function, and then the next phase starts, and so forth. So if you have something where you're essentially doing this in a loop, my pet example is you're rendering streaming video, and you've got audio coming in, you've got frames to decode, and you might have various bits of depending how the video is encoded, you might have various bits of the frame to process, and you've got you've got a full frame worth of data. You've divided the processing of the frame and the audio that goes with it amongst multiple threads. When the whole set is ready to ship out, then you call the completion function, which sends it to the renderer to actually display. And then your full set of threads can then move on to the next frame. Obviously, whether or not real streaming engines do it like that is entirely beside the point. I think that the concept that you have this looping pattern is the driving point there. So our barrier API, again, is quite straightforward. We have a barrier, and the template parameter is the task type. And by default, it is a implementation defined task type, which is default constructible and does nothing. So you can't create a default barrier with a task of any that actually does anything, but you can pass. You can use standard function of void with no parameters as your task type or something like that, and give it a task. In principle, there could be a deduction guide that allowed you to deduce it from a task, but there isn't one. So anyway, you can give it a task type that specifies what sort of task it's going to run. You then actually give it the task in the constructor along with the count. You can arrive at the barrier, and that gives you an arrival token, which you can then pass to wait when you're at the point that you actually want to wait. So this allows you to sort of to trigger other threads before you wish to wait yourself, and sort of split things apart. Mostly, you're probably going to call arrive and wait, which literally just calls wait directly on the result of the arrive, and therefore and potentially avoids the creation of this token, which it might be expensive. And then there's this arrive and drop, which allows you to decrease the count permanently, and whilst triggering the waits on everybody else, but doesn't wait this thread. This thread doesn't wait now, and it no longer is a participating thread in this barrier, so it can't wait again, can't arrive again if you've called arrive and drop. So it's worth noting at this point that things like NVIDIA GPUs that have a high concurrency value. They do support C++20 library. They have special instructions for barriers and latches. And so calling arrive and wait rather than x.arrive and x.wait separately is worthwhile, because if you do that, it can use the special instructions, whereas if you separate them, it can't, or at least not in quite the same way. The compiler can't optimize it as well. So if you don't need to do the separation, don't put the separation in there. So yeah, a barrier is fundamentally for loop synchronization. You've got a series of things that need to happen, and then when they're all done, then we can finalize the set and then move it on, and then all the threads reset and process the next bit of data. And it's important to note that the completion function is run on one of these participating threads that's actually waiting for the barrier to complete. But you don't know which one. And so you can't decide in advance, I want my completion function to run on thread 3, because that's the one that I know I've scheduled on the with the right priorities and stuff. No, you don't have that control. If you wait on 5 threads, one of those 5 threads will run the completion function. It's probably the one that arrived last at the barrier, but not necessarily. Depending on how the OS and the library have scheduled things, they might decide, oh, it's actually the one that arrived first at the barrier gets a special flag that says, I'm going to run the completion token, the completion function, or something like that. It's up to the library which one it is, and you don't have any control. Okay, so what does it look like in some code? Well, we have some number of threads and a task to finish, to finish things off. Like I said, you can give it a task type. Standard function works. The new C++23 function ref will work, or you could actually just give it a type of a function pointer type. And so you give it the number of threads that you wish to count, and then the completion function, and then each worker thread it sits in a loop while it hasn't been asked to stop. Then it's going to do stuff for the current phase. Then it's going to arrive and wait at the barrier. Then when all the threads have finished their current phase stuff, then we're going to loop round. And if we still haven't been asked to stop, we're going to do the stuff for the next phase and so forth. So what if you don't have a loop synchronization problem? You've just got some data that you're generating on thread 1, and you want to pass it to thread 2 in a nice synchronized fashion. Well, futures are one way of doing that. They are a one-shot transfer of data between threads. And they're one-shot in 2 aspects. The first is that each future can only hold 1 value. And so if you want, once you've given it a value, then you need to create a new instance of things to pass a second value. So if you're after stream, then you need something else. But if you've got a single value that you wish to pass, then futures are great. 3 ways of using futures. First is you can use async, which typically it is used so it wraps a task that will produce a value, and the result of that task is returned in the future. How that task is run depends on the way that you call standard async. You can make it run that task in a new thread, or you can make it run that task in a deferred fashion, which then only gets run when somebody actually asks for the future for its value. This was a C++11 compromised way of how we could sort of get thread pools without really having a thread pool. In practice, it doesn't work very well. So you use standard async when you want to start a thread now that's going to run and produce me a value, and then I can get the value in the future. If you're not doing that, then don't use async, use something else. Possibly package task, which essentially does the same thing, except you're in complete control of the threads. Okay, so the second one is promise, where you're explicitly setting a value. You have a promise, and then from it you get a future, and you explicitly set a value, and then the value gets transferred to whoever's waiting for the future. And then the third thing is package task. In this case, you give it a task, and it just stores the task and says, fine, I'll store this task. Call me when you're ready. And you can then get a future from that package task. And at some point, you can then invoke it. It's a callable object, and it will then run the task that you gave it. And then the result is then stored in the future. So you can use that with thread pools to run a task on a thread pool that will give you a result that you can get in the future. And all of them will give you a future of some type T for the result. So our future of T, what's its API? Well, you can create a default constructed future that holds no object, it has no state. This is what you get if you retrieve the value, you now have an empty future. If you move a future from one instance to another, then the source is now empty and has no state. You can check, is it valid? Has it got any state? And that's a check that you can do. You can wait for the data that's there that's to be ready. Obviously, if you wait for something that has no state, that's an error. It will throw an exception. If you don't want to just do an open-ended blocking wait, you can wait for a duration. Say, I want to wait for 3 milliseconds. Or you can wait until a point in time. So if you're writing some semi-real-time code where you have a hard deadline, I must be completed in my operation by this point. Then at the beginning of your function, you can calculate what the end time is, and then you can use that same time point as parameter to any weights you've got within your function. And then all your weights will know, they will return whether or not they were successfully weighted by your deadline. So wait for and wait until return your status that say, was it actually ready or not? And then obviously we can call get, which will wait for the data and retrieve it. Obviously, if you already called wait or one of the wait for or wait until and it said the data is ready, then get will return immediately. If the data wasn't already ready, then it will wait first and then return you the value. So you could then have the option of doing blocking or non-blocking. You can call wait directly and then call get. But because get does an implicit wait, you can omit that initial wait if you want to, depending on how you're structured. If you might want to wait for the thing to be ready, then do a bit of stuff in preparation for how to handle it, then call get. So you might want to do that split, or alternatively, you can just omit the wait. The other option is that you can wait for a time and poll. So you can wait for 0 seconds, which will then just return immediately and tell you whether or not the data was ready. And then if the data is ready, if it returned future status ready, then you can then call get, and the get won't block, it will just give you the value. So if you're going to use futures, you need to know how to get them. And so promise is probably the way you will use it in most cases. The default constructor creates an object which has an empty state. It's ready to receive a value, but it doesn't have one yet. You can check whether it's got a state that's ready, ready to accept a value by calling valid. Then you can set a value on it, or you can set an exception on it by using an exception pointer. So you can put like a try catch, try set promise, promise.set value, my function. And then if the function throws, then you can then have a catch that catches the exception and then calls set exception, current exception. And so that will store the exception pointer in the promise. Then when someone calls get, it will throw that exception. So it transfers the exception across threads using the exception pointer mechanism. And then, of course, if you have a promise, you want the future, so you can call get future to return the value. So I put that in some code. We have our promise, we get a future from it. We're creating a thread. So we're going to move the future into the thread, because futures are one shot, so they have to be moved. You can't copy a future, you can only move it. And in that thread, we're going to call get to wait for the value to be ready, and then call our do stuff function. And then our second thread, we're going to take that promise by reference, or we could have, again, moved the promise in. And then we're going to set the value. And when that value is set, then thread 1 will wake up, it will get the value, it will call do stuff with the value. The values are all passed around by R value reference, so that in do stuff it gets an R value that it can move from. So it's actually can be quite efficient. You can pass move only things through set value and get. And likewise, if you pass an exception in, which it doesn't have to be called from current exception, you can create your own. Actually, say I want to throw an exception of this type. So I'm going to create an object and call make exception pointer to get an exception pointer to it, pass it in, and call get and the other thread. And this time it will throw. So it won't call do stuff. It will throw the exception that was passed in. Or we can call it. So if you don't want to use promise, you can use async, and this works like JThread. You pass it a callable and some arguments, and it copies it into a thread. You want to pass the standard launch async as the first parameter. If you don't specify that, it is up to the implementation whether or not it starts a thread for you. And as I already said, you probably don't want that. You don't want to suddenly find that when you call get, it's going to actually run your other function inside the get, which you weren't expecting at all. So you do want to pass that standard launch async as the first parameter. The features that come back from standard async are slightly special as well, in that like JThread, the destructor will wait for the thread to exit. Even if you don't explicitly wait or get on the future, it will wait for that function, that thread to exit. So you need to be aware of that. And so prior to the adoption of JThread, I would recommend that people use async precisely like this in order to get that waiting behavior. But now we have JThread. JThread is the superior option because JThread gives us the stop tokens, whereas async doesn't. There's no interaction with stop tokens when you're using async. So futures are one shot. So after you've retrieved the value, they are no longer valid. The valid function will return false and get will throw. So they really are, you can only get that data once. If you do want to get the data multiple times or you want to retrieve it from multiple threads, then that's what shared future is for. And you get this by calling share on your future. So if you've got a promise, you call prom.getFuture to get the future, and then you call .share. And now you have a shared future that you can copy. And all copies will become ready together. And they will all return the same value, which is now returned by const reference. So if you can't use it directly in place through a const reference, then you need to copy it. And if it can't copy it, well, then don't use shared pointer and shared future with it. But so now we can have two threads, thread 1 and thread 2, that both have a copy of our shared future F, and they both call get, and that's all fine. They will both get the same reference to the same object. I hope that everything's fine. So yeah, if you can use futures, futures are better than mutexes, but often you can't because they're one shot. So we use mutex. Mutex is short for mutual exclusion. It is a means of preventing concurrent execution, so we want to use them sparingly if we can. And obviously, the simplest way to make sure that all your data access is secure is that any time you access any data that might be possibly shared, you lock the one and only mutex, and then when you're done accessing it, you unlock it. But obviously, that leads to essentially one great big single-threaded program with a lot of extra overhead for managing all the state transitions. So we try not to do that. That's the approach that Python uses, global interpreter lock. We generally want to have finer grained stuff than that. So C++ provides 6 mutex types. I think that is 5 too many. We have standard mutex, which is the one you should use in all cases. And then we have various others. If you find you need a recursive mutex, then your code is probably structured wrong. If you need a timed mutex, then, well, maybe you need it. Maybe you've got some sort of soft real-time time deadline and you don't want to block, but probably you're better off using some slightly different mechanism so that you don't have any form of blocking within your time loop. Shared mutex in theory, is a means of optimizing the case where you have multiple threads that want to read the shared data and only one thread that wants to write the shared data, or occasional threads that want to write the shared data. In practice, shared mutexes can actually make your code worse. So if you're going to try and use it, then you really, really, really need to profile. So I would say 99% of the time, you think you want to share mutex, don't bother, just use a mutex until your profiler tells you that actually there's a problem. So yes, if you're going to use mutexes, use standard mutex and be done. Unless your profiler tells you that there really, really is a problem. And then you might be able to restructure your code to avoid that anyway. Because contended mutexes are where the performance hits are. And if you have a contended mutex, then every single one of the options is going to be bad. So restructuring your program to avoid the contention is probably the way to go. Likewise, for locking and unlocking, then we have nice RAII types. We have 4 of these. Again, use scoped lock unless you have a very good reason not to. So the one at the bottom, shared lock, is the read side of the shared mutex. So if you're trying to, if you've opted to use a shared mutex because you really, really think it's going to be beneficial, and you're on the read side, then you use a shared lock, which allows multiple shared locks to be acquired on the same mutex at the same time. Whereas the right side would then use a scope lock to say, I am the unique right side. And then you can either have multiple shared lock owners or one scope lock owner. Unique lock and lock guard are like scope lock, but they're the C++ 11 versions. And you probably don't want to use them. Apart from occasionally you have to use unique lock because it has some nice things like movability, which scope lock and lock guard don't have. But mostly scope lock is your friend, and that's the one you should use. So we have some data that's protected by some mutex, and we want to update the data. So we use our scope lock to lock the mutex. It's an RAI type, so we lock it. It locks in its constructor. It unlocks in the destructor. We can access the data in between. Everything is straightforward. It is a template, but there's a deduction guard, so you don't need to specify the type of your mutex. You just say scope lock on some mutex. See, sometimes in your code you need to lock multiple mutexes. If you take the classic example of an account where you're transferring between 2 accounts, and then you've both got mutexes to protect their data, you want to lock both of them. If you lock one and then the other, then we have a potential for deadlock. Because if you're transferring from account 1 to account 2 at the same time as somebody else is transferring from account 2 to account 1 on a different thread, they both lock the same 2 mutexes on account 1 and account 2, but in different orders. And so that is a potential for deadlock. Scope lock says, don't do that. Just pass them both in. I want to lock 2 mutexes. Give me 2 mutexes to lock. I will work out how to avoid deadlock. The library will do that for you. You do not need to care about the order. You can pass the same order on different threads. You can pass different order on different threads. It doesn't matter. If you pass the same set of mutexes, it will avoid deadlock if you use scope lock. So this is really nifty. Obviously, if they're locked in different scopes, then you can still do that because you can't pass them both in together. So you still need to be aware of that. And the general rule is don't call unknown code whilst you've got a mutex locked, because you need to know which mutexes that code might lock. But in general, if you need to lock multiple things, pass them both into the same scope lock and it will just work. Well, so if we use things like latches and barriers and futures, then they have nice means of waiting for stuff. A mutex, if you protect data with a mutex, there isn't immediately an obvious way of waiting for stuff, waiting for the data to be ready. You can't call mutex.wait because, well, what's it waiting for? It only knows about the lock itself and not about the data. So how do you wait for data to be ready? Now, obviously, the daft thing to do is you write a busy wait, and you just have a loop, and you have a scope block, and you say, is my data ready yet? No. Okay. Is my data ready now? No. Is it now? No. Okay. And this just, no, this is a bad idea. I hope that it's obvious to all of you that this is a bad idea, because it just wastes CPU time and actually potentially makes it take longer for the data to be ready, because the mutex has now got contention. And then it wastes electricity, which is wastes power and is not very green. So don't do that. So if you need to wait, this is what we have condition variables for. They are the friends to go with mutexes. They don't provide any synchronization benefits. That's what a mutex is for. But what they do is they help you avoid busy waits. They're an optimization of a busy wait loop. So this is where you need a unique lock, because condition variables don't work with scope lock. They work with unique lock. Again, it's a template. Again, the deduction guides mean you don't need to specify the template parameter. You lock your mutex, then you call condition variable wait function, you pass in your lock, and you pass in a little lambda or other function that says what you are waiting for. And then it will only return from wait when your little lambda returns true. It will work out how best to do the waiting, and it will make sure that it always has the lock locked when it calls your lambda. And it will keep it, if your lambda returns true, it will keep that mutex locked when it returns. So you have it locked when you start, and it will return with a locked, but it will unlock it in between. So that it would be a legal implementation of it to make it the busy wait loop we saw back here. That is essentially a legal implementation of a condition variable wait, but it won't do that because the OS knows that that's a bad plan. So, it will unlock and then relock the mutex, possibly multiple times, and then it will check your function, and when the data is ready, it will return. But it doesn't guarantee how often it checks it. It might never check it unless you call notify on the other side. So on the other side, we have this notify function, notify1, which wakes just one function, one other thing that's waiting on our condition variable. There is a notify all, so if you have multiple threads that are waiting, it will wake all of them. So depending on what you're using, then you might do either. So we can use scope block on this side because we're not explicitly interacting with the condition variable. We lock our mutex, we make the data, we unlock the mutex, then we notify. And you're allowed to notify whilst you hold the mutex, but that just adds an extra bit of delay because the notifying thread still ends the mutex. It wakes up the other thread. It says, "Oh, can I have the mutex locked so I can check whether the data's ready?" It says, "No, you can't because I still got it." Okay, I'll now have to go back to sleep again. Then the thread that's notifying unlocks the mutex. Then the other thread finally says, "Oh, now I can have the mutex," but you've probably lost a time slice or two. So if you unlock first, then you notify, then it wakes up as soon as it's ready. And it avoids that little bit of contention on the mutex. So we have that, we notify data, and then we'll wake up. So that's all straightforward. If you have a busy wait loop and you're trying to integrate cancellation tokens, then they're straightforward because you've got access to that loop, and you can say, "No, well, if someone asked me to stop, then I can just stop." But if you've got a condition variable, you can't do it with a normal condition variable. You have to reach for condition variable any. It's got this extra suffix on the end, condition variable any. And then you can pass in your stop token into the wait loop as well. So you say condition variable wait with a lock and a token and a predicate, and then it will return. And now it returns you a Boolean, and that tells you whether or not your predicate returned true. And obviously it returned false, then that means that I had to exit this loop because somebody asked me to stop, rather than because the data was ready. And so at this point, you say, well, in this particular case, I'm just saying, okay, fine, I won't process the data, I'll just return. You could do something else. No, I don't know, depending on what you want to do in response to a stop request. If there's you were asked to stop at the same time as the data was ready, then it will return true. And so you might then want to check whether the stop was requested explicitly, depending what you're then doing. If what you're doing with the data is really quick, then it's like, well, I know that the data is ready now, so I'm going to process it anyway, even though they asked me to stop, because it's a really quick operation, and then I'm just done, rather than partially done. So it's up to you what you do. But you have to use this condition variable any, because it's a little bit more complex on the implementation. Because stop token is not a native OS thing, whereas some condition variables are, then condition variable any is then a wrapper on top of the OS thing that integrates with stop tokens. So no, it does. It also has other things. It works with shared mutex locks and things like that as well, but which is where the any originally came from. But because we're not using those, because we don't need to, we're just using plain mutexes, then condition variable any is used so that you can integrate with stop tokens, which I think is really nifty, and that is an advantage you have over future weights and latches and barriers, because they don't integrate with cancellation tokens at all. So this is an advantage here. Okay. If none of these synchronization primitives do what you want, and really, I think they probably do. If you think about it hard enough, they probably do what you want. But if none of them do, then you can reach for semaphores. Semaphores, now, fundamentally a semaphore, it represents a number of available slots, and you can acquire a slot and you can release a slot. And there is no requirement about which thread acquires and releases. You can have one thread acquires 5 slots and then 5 separate threads release the slots. No, there's no requirement about that. If you try and acquire a slot and there isn't one because nobody's released it, it's not available yet, then you will block. And if someone releases a slot whilst another thread is waiting to acquire, then it will wake up the waiting thread. That's the straightforward thing. You can build just about anything with a semaphore or a combination of semaphores. There's an online free book, The Little Book of Semaphores, which is actually not so small, it's a few hundred pages, that tells you how to do just about everything with semaphores, including mutexes, condition variables, cancellation, everything. You can write, if it's a multi-threaded synchronization primitive, you can build it with a semaphore if you must. They are a low-level building block. But mostly, you're better off using the higher-level structures that your library already provides, rather than building your own with semaphores. So, as a special terminology, then we have a binary semaphore, whereas normally we just have a semaphore. We have a binary semaphore which has 2 states, and therefore it has 1 slot or no slots. And that's very much like a mutex. So you could use it as such. You could implement a mutex with a binary semaphore and put the additional constraint on yourself as a user that I'm only ever going to call release from the same thread that called acquire. But that wouldn't be required by the semaphore. The semaphore would allow you to release it from a different thread if you really wanted to. So in C++ 20, counting semaphore is the general template with a max count, and binary semaphore is an alias for counting semaphore of 1. It might be a specialization with special instructions or whatever, but alternatively, it might just be use of the general template. And so, like mutexes, we have a mutex. Then, if you use a timed mutex, then you have you can try and lock for a certain period, and with semaphores, we can do our full blocking acquire, or we can try and acquire for a timeout, or until a certain time, and those will obviously return false if they didn't succeed in acquiring the semaphore. So we might create a counting semaphore with 5 slots and initially say all 5 are available. And so you could create a semaphore with 5 slots and say none are available, or 2 are available, or 1 is available, or whatever. It's up to you how it fits in. And if you look at the little book of semaphores, and there will be reasons why you would choose different starting counts for different semaphores. But if it's initially 5 available, then in our function, acquire and do stuff, then at most 5 threads. So even if we call func from 100 threads, at most 5 at a time will be calling do stuff. Obviously, as each one drops out, then somebody else might pick up the count, and so it might be that there's always 5 threads calling do stuff simultaneously, and that which 5 threads it is varies. But that's what it does mean, that at most 5 threads can be there. But yeah, no, you can do anything with semaphores. It's a low-level thing, but please don't, because it makes it complicated. It's much harder to review code with semaphores than it is with mutex locks. Okay. The final low-level thing in our box of tools is atomics. And they are low-level synchronization primitive. They probably relate directly to hardware instructions in some way, particularly if you use simple things like ints. But it's a template, and T can be anything that is trivially copyable and bitwise comparable. So if you can mem copy it and mem comp it, then you can use it. And that can be a struct with 1 million chars in if you like. But don't expect that to be hardware instructions. That's going to use a mutex. Okay. The exception to that is that to being trivially copyable is it could be a shared pointer or a weak pointer. Those are sufficiently useful that there's specializations for them. Timo did a talk about the implementation of those earlier in the week. So if you care about using those, then watch the recording of his talk. Atomics may or may not be lock-free. On most common platforms, then most of the built-in types will have an atomic version. So atomic of integral and atomic of pointer will probably be lock-free for any integral or pointer type. The only guarantee that is lock-free hardware instructions is atomic flag, which is a sort of cut-down Boolean, which has limited instruction sets. Then there is a signed integer of unspecified size, atomic signed lock-free, an unsigned integer of unspecified size, atomic unsigned lock-free. But for any given type T, you can query if is it lock-free with atomic T of is always lock-free is a static context for a Boolean. And so if that turns out to be false, then you're probably better off using your own mutex than using the atomic of T. But you might decide that for portability's sake, then I know that on most of my platforms, then it really is hardware instructions, and I can cope with using the implementation mutex on the ones where it isn't. So, yeah, atomics are low level. They have a variety of operations on load and store, and integrals have operators like plus equals and minus equals and bitwise ands and ors and things. And obviously a crucial one is exchange and compare exchange. If you're thinking of using them, then you really need to read up about them and think carefully about all the consequences and everything. They are low level in the box of tools. So yeah, don't use them unless you have to. And again, yes, unless you have to means you ran the profiler. The profiler said, it's my synchronization that's taking all the time. And what I'm synchronizing is only something that's bitwise copyable and bitwise comparable. So maybe I can use an atomic and see if that helps. So yeah. Most of this stuff is covered in my book, because even though it's not C++, there isn't yet a C++ 20 edition, most of the things are in the Concurrency TS, which is covered in the second edition. There is a C++ 20 addendum, which will be available as a downloadable PDF for anyone who's bought the book, but it's not yet available. At some point, I'm going to get the round with the editors and get that all finished and sorted and uploaded, but it's not there yet. Anybody got any questions? Yes, over there.
So you mentioned at the beginning of the talk that it was mainly for new projects that we start with C++. But if you come from existing projects that's already using Future and Async, when you migrate to C++20, is there a big advantage using Gthread and just changing the architecture a bit to?
Okay. Yeah. Okay. So the question is, if I've got an old project that already uses async and future, is it worth switching to JThread? And as ever, as a true consultant, it depends. Sure, if you are using JThread and future, well, so firstly, I'd say if the code you have works, then it's still valid code. Don't change it unless you have to, because there isn't any direct performance gains or necessarily any maintainability gains just from changing the code. If, on the other hand, you are changing the code for you're changing that bit of code for some other purpose, then if you're only using it for the waiting facility, then yes, change it to a JThread rather than async and future, because it makes it more explicit what it is that you're doing. You're waiting rather than passing a value. If you're passing the value, then async and future is exactly what you want. So no, use that. And again, if you're wanting the cancellation benefit from JThread, and you're saying, well, actually, I've rolled my own stop token, using a Boolean flag or something, and I want to use standard stop token, then, well, you either have to pass that in through standard async yourself, or you can switch to JThread and let JThread manage it. And so if you're wanting that benefit, then yeah, there's a benefit there from switching. But yeah, if your code works, then there's no inherent benefit from switching just because. Yes.
I'd like to respond to that slightly, because there is an inherent benefit if you have developers that are familiar with the standard library rather than your own utilities. Okay.
Yes. Yes. So I guess that's particularly if you are using things like stop token and you've rolled your own, then using the standard library is always a benefit, because yeah, new developers will come in and they will be able to use your code, and whereas other people, anyone else would then have to learn what you've done yourself. But if you're still using standard async, it's still part of the standard library. But yeah, any additional facilities you've got alongside that have now been replaced by standard components, then switching to the standard versions is worthwhile for future maintainability. Yes. Okay. Any more questions from anybody? There is one on the Q&A. Okay. Oh, so there is. Okay, Lucian says, recommend using standard mutex instead of shared mutex. How bad is the performance of shared mutex in non-contended cases? And the answer to that is you will have to profile what your platform does. I think that, for example, the Microsoft standard library implementation, if I remember rightly, actually is better with shared mutex than standard mutex, whereas on Linux, it's the other way around. But I might have misremembered, and I don't know quite what the performance difference is. It might be so trivial that it's not worth changing. And I think in the first instance, as ever, choose standard mutex until your profiler tells you that is a bottleneck and that you're spending significant amount of time locking and unlocking. And then think about what the other options are. Okay. Any more questions from the room? Any more questions on Zoom? Okay, yes.
Just to know if the thread was
So the question is the thread executors supposed to be available soon? Well, we were hoping that they would be in C++ 23, and they won't be. We're expecting that the library evolution group will pass the executor proposal to the library group for C++ 26. As soon as C++ 23 is out the door, then we're expecting to have a look at doing that. Whether it will then indeed be finished for C++ 26 is something that I certainly can't predict. I certainly hope it would be. In the meantime, then there will be publicly available versions available for download, like libunifx. I think HPX are planning to include something along those lines, but don't talk to me about what they're planning. And there are, if you look at the P2300 paper, which is the paper proposing the executors, then there are links to available implementations that that are available for use of varying completeness and production readiness. So yes, there will be versions that you can use, but they will not be standard for a good few years, unfortunately. So there was also a question on Zoom, so I'm just having a look at that. Yes, Victor says shared mutex is better on Windows because there's a newer implementation and the old one is stuck by ABI. Yes. And yeah, Lucian said that the authors of P2300 do provide a reference implementation. So yes, that will be one of the available ones. And again, yeah, it's not quite 100% complete yet, but obviously they're trying to have it as a reference implementation, so it'll get there. So yes, thank you for that, Lucian. Okay. Any more questions? Okay, then I will just do a brief summary, which is firstly, avoid managing your own threads if you can. Use the parallel algorithms if that works for you. Use third-party thread pools if you can, because it saves you the headache of managing the threads and potentially makes your code more scalable. If you're managing threads yourself, use JThread unless you really can't. Use stop token for cancellations because it's great and it's standard. So there is that clear benefit over homegrown things. And stop callback just means that it then can integrate with just about anything. If you need to pass data around and synchronize data, use future latch and barrier if you can, because they're nice. And if you need to do more in the way of synchronization than you can get with those, use standard mutex unless you have a good reason not to. And occasionally that good use and not good reason not to might lead you to low-level stuff like standard atomic. But think very hard before you go there. Okay, that is all I have to say.